good morning, everyone. My name is Luca. Thank you for the kind invitation, Max, for this seminar. So currently, I'm a postdoc at the Radboud University in the Netherlands, and I'm here to present you this joint work with Max Gadulot from the University of Durham, UK, and Stefan Picek, who is currently my supervisor at Radboud University, which is about like a kind of a bumpy story of a paper that just got published on Design Codes and Cryptography a couple of months ago, which is about, let's say, a new construction of bent Boolean functions. So this will be roughly the structure of my talk. So I will first give like very small introduction about what was the backstory of the publication of this paper. Then you will see that it is like kind of a complicated construction. So we'll start like from the beginning, talking about the first version of our construction that was based on cellular automata and mutually orthogonal Latin squares, then showing the actual construction, and then showing, let's say, a simplified construction of these bent functions. So let's start. So I call this an unlucky paper in a sense, because you can see here that it has been published on August 13 of this month. But actually, if you go to see like the timeline of the peer review, it's been quite difficult to get it published, because actually we started already at the end of 2019 of working on this, and we had a work in progress paper and we wanted to submit an extended abstract to BFA. So we submitted it at the end of 2019. Actually, it was rejected in BFA, which was already kind of weird, because usually BFA accept like extended abstracts. So usually you are not like saying, let's say, so picky about the details of your paper. But actually they were right, because we were missing a detail in our construction. Then we tried directly with cryptography and communications, and we submitted at the end of 2020, and then got almost immediately a reject on the ground that the construction now was correct, but in their opinion of the reviewers, it was not enough interesting or novel. And then we tried with design codes and cryptography, trying to tone it down even more, what we were accomplishing. And then we had first a major revision in July 2021, and then we had like a lot of minor revisions until at the end we finally managed to get it published in July 2022, August 2022, sorry. So let's see how this bumpy ride went. So, okay, Boolean function, I guess that you all know about it. So I won't be stopping here a lot, but just to give you like an introductory slide. So they are used for string ciphers, for block ciphers, for example, to design key string generators, or as coordinate function of S boxes in block ciphers. And the basic representations that usually one adopts for Boolean functions is the classic truth table, which is 2 to the n bit vector that specify all possible output values of a Boolean function, such as in this case with 3 input variables, we have 8 possible values in total. The algebraic normal form, which is a sum, which is intended as a sum modulo 2, so an XOR of products, which is a logical AND. And then the Walsh transform, which basically measures the correlation of a function with the linear function a dot x, where a dot x is the scalar product. And here you can see the total Walsh spectrum of this Boolean function in this example. Now, bent function in particular, they are very interesting for Boolean, for cryptography, because basically they reach the highest possible nonlinearity, and this is an important property for resisting, for example, linear cryptanalysis. And in particular, they are defined on the basis of what is called Parseval relation, which holds for all possible Boolean functions. So we know that the sum of the squared Walsh spectrum is constant for all possible Boolean functions. So the bent functions are actually those that get like the minimal Walsh coefficients, so plus or minus 2 to the power of n divided by 2 for all possible coefficients. And you can see here an example with 4 variables. In this case, we have all coefficients that would be either plus 4 or minus 4. And in particular, you can see that these functions exist only if n is even, because you are dividing the coefficient, the exponent of the coefficient by 2. So you cannot do it for all, for another number of variables. And they're always unbalanced simply because if you compute the coefficient in the null vector here, the function is balanced. So the truth table is composed of an equal number of zeros and one, if and only if that coefficient is zero. But since we already said here that all coefficients are plus or minus 2 to the power of n over 2, it cannot be balanced. So for constructing these kind of objects, we have several ways that have been already published in the literature in the span of more than 4 decades now. So if we set, let's say, n equal to 2 times n because we want n to be even, then one of the most famous construction is the so-called Maiorana-McFarland construction, where we define f in terms of 2, let's say, subvectors of length n over 2, so n in this case. And the function is defined in this way, where pi is any permutation of f2 to the m, and g instead is any function of m variables. So if we define this as the dot product of our first input vector x, oh, sorry, I do not have to go too close to the screen because it is a touch screen. So we define this as the scalar product of our first input vector x by the vector given to us by the permutation pi, XORed with the function g over the second vector, then we get a bent function. And another construction, or let's say a more general class of bent function, is the class of partial spreads that was introduced by Dillon in his thesis in '74. So we say that basically f belongs to the partial spread class ps minus, or respectively ps plus, if we can define the support of the function. So basically the set of vector which map to 1 in the truth table of the function in this way. So we have a family of 2 to the power of m minus 1 n-dimensional subspaces of f2 to the n, where each pair of these subspaces have a trivial intersection, so they have only an intersection on the null vector. And then we do the union of all these subspaces in our family, in our partial spread, and we remove the null vector from each of them. Then the resulting vector will be the support of a bent function. The same thing is done for functions in the class partial spread of ps plus, where instead we just do the union of all possible subspaces in the spread, but we need in this case 2 to the power of n minus 1 plus 1 n-dimensional subspaces. So in particular, the new construction that I'm showing you is about partial spreads. So it's a construction that gives functions in the partial spread class. Now, let's start with the first, let's say, the first act of this construction, which starts from afar, let's say from cellular automata and mutually orthogonal Latin squares. So what is a cellular automata? Basically, we consider it as a vectorial function, f, from fq to the n to fq to the m. So fq is the finite field of order q. And this function is defined by uniform output coordinates. In particular, what does it mean? If we consider this example where we are in the binary field, so fq, and we have n equal to 6, we define, for example, what is called the diameter of the cellular automaton as 3, which means that the output coordinate will be defined over 3 variables only. And it is like local in the sense that it is defined for each possible output coordinates, like in here. Basically, we apply the same local rule to the neighborhood, which is of width d, let's say. So here we are considering the function f, since we are over f2, so it is a Boolean function in itself. So it is the XOR of the 3 variables in the neighborhood of diameter 3 in this case. So we apply here the XOR of 1, 0, 0, and we will get a 1. Then we shift like here by 1 place our window of width d, and we compute 0 XOR 0 XOR 0, then the same here, and then the same here for 0, 0, 1, and we get all output coordinates in this way. So in this case, we are considering a no-boundary cellular automaton, which means that we are applying the local rule up until we have enough right neighboring cells. So the output will be smaller than the input in this case, of course. In the periodic case, which we won't address here, but it's very common in the cellular automata literature, basically we see the input vector as a ring, so with circular boundary conditions, and we can apply the local rule over all possible cells, because in each case, the first two cells will be like the right neighboring cells of the two cells here. Okay. Okay, so this is how cellular automaton, a binary cellular automaton works. Now, Latin squares, on the other hand, are very important combinatorial construction or object, let's say, that is studying the combinatorial design literature. So basically, they are, let's say, matrices of size n, so n by square matrices of size n by n, where each row and each column is a permutation of the set of the first integer number from 1 to n. So in each row, we see all numbers from 1 to n, like in this case, 1 to 4, because we have n equal to 4. And the same goes also for the columns. And then we say the two Latin squares of the same order are orthogonal if by superposing them, so we put one on top of the other, like in this example, then we get all possible pairs in the Cartesian product of the set of the first n integer numbers, positive integer numbers, by itself. So in this case, we get all possible 16 pairs. We say that if we have a set of Latin squares which are pairwise orthogonal, then we call it a K-moles, where K is the number of Latin squares in the family. Moles stand for mutually orthogonal Latin squares because they are orthogonal in pairs. And these K-moles are also equivalent to another combinatorial object, which is an orthogonal array of parameters n to the square k and n2, which I will go over a little bit in detail later. So for the moment, it does not need to concern us. Now, how do we construct these Latin squares with cellular automata? So this was one of my work during my PhD at the University of Milano-Bicocca. In particular, there I was interested in trying to construct secret sharing schemes using cellular automata, and actually it turns out that Latin squares and orthogonal arrays are combinatorial structures that are related to these secret sharing schemes. So this was the original motivation, and then we use this to construct the band function that I will show you later. So we say anyway that a cellular automaton is bipermutive if the local rule is defined in this way. So we have our function f over diameter of width d. And then the function is basically the sum, where this plus here is over the ground field fq, of the leftmost variable x1, the rightmost variable xd, plus any function of the d minus 2 central variables. Okay, and we call this phi the generating function, but this is just a terminology. And now if we start from a no boundary cellular automaton, which has like a initial width, so an initial input vector of size 2 times d minus 1, where d is the diameter of the cellular automaton, with a bipermutive rule of diameter d, then this can be used to generate a Latin square of order q to the power of d minus 1. And how is it done? So basically we use the first half of the input vector to index the row of a Latin square, the second to encode or to represent the column of this same square, and then the output of our cellular automaton here, which will be of width d minus 1, because we started from something that has width 2 times d minus 1, and we are applying a local function of width d. So we use this output as the entry at these coordinates x and y. And if the function is defined in this way, which is kind of a very general definition, we just need the plus here and here for the leftmost and rightmost variable, then this will be a Latin square. This is to give you like a short example using again diameter 3 as an example. We have a cellular automaton with the same local rule that is XORing the 3 variables in the local neighborhood. This is also called the rule 150 in the cellular automata literature, simply because 150 is the decimal encoding of the output of the truth table of this function. And if we use like this encoding for pairs of bits, because in this case, q to the power of d minus 1 will be 4 in this case. So we need pair of bits to encode, let's say, the first half the second half and the output. So we have 0, 0, which is mapped to 1, 1, 0 to 2, 0, 1 to 3, 1, 1 to 4. And then we compute our cellular automaton over all possible 16 input vectors. Then we get these Latin square related to this particular local rule 150. Now, in order to get like also the orthogonality, I focused in the PhD on a subset of bipermutive cellular automata, which are linear cellular automata. So in this case, we consider a local rule, which is a linear combination of the cells in a neighborhood. So beside having like the sum of the first, of the leftmost and the rightmost, let's say, variables in the neighborhood, we have also a linear combination of the central cells, okay? And in this case, we can associate in a very natural way a polynomial to this local rule, because we simply use the coefficients that lives like in the ground field F2 as the coefficients of the increasing power of the monomials in the polynomial Pf of x in this case. And also the global rule, so if we take the whole cellular automaton, which is mapping an input vector of with, let's say, n to an output of size n minus d plus 1, then we can describe this linear cellular automaton with this particular transition matrix, which is of size like n minus d plus 1 rows and n columns. So we start here from the top left by putting our coefficients from A1 to AD of the local rule, and then we put all zeros in the remaining positions. Then we put a 0, so we shift one place to the right, and we put again our coefficients, and then we fill everything else with 0. And then we continue to shift up until we arrive here at the end, okay, for constructing the subsequent rows. And then the cellular automaton would basically amount to the multiplication of this transition matrix MF by the transpose of the input vector X. Of course, a linear rule actually is bipermutive if and only if these A1, AD are different from 0, and in particular, they're equal to 1, because we want our leftmost and rightmost variables to be summed in our function in order to ensure that we get a Latin square. Okay, so now if we consider two linear bipermutive cellular automata, and we consider their transition matrices, basically we can observe that these two cellular automata will generate orthogonal Latin squares. So they generate Latin squares on their own because they are bipermutive, and that's it. But they will be orthogonal if and only if this matrix is invertible. So we put the transition matrix of the first one and the transition matrix of the second one, of the two cellular automaton, one on top of the other. And this is actually will be invertible if and only if the two associated polynomials will be coprime. Why? Because this is what is called the Sylvester matrix related to the two polynomials defined by the coefficients A1, AD, and B1 up to BD. And it is a well-known fact that the determinant of this matrix, which is also called the resultant, is non-zero if and only if the greatest common divisor of these two polynomials is 1. So basically what we showed in this work that was already published in Design Codes and Cryptography in 2020 is that if you get a set of T linear bipermutive cellular automata of diameter D, then they generate a family of T moles of T mutually orthogonal Latin squares if and only if all their associated polynomials of their defining rules are pairwise coprime. So here you can see this example of these two rules. So rule 150, which we saw in the first example, rule 90, which has this associated polynomial. They are coprime over F2, so we get these particular orthogonal Latin squares. And then in that paper on Design Codes and Cryptography, which was, let's say, the preface of this construction that I'm showing you now of band function, we consider also combinatorial questions about like counting the number of coprime polynomials over, in particular, over F2 of degree n and non-zero constant term, because we want the polynomials to be of degree n and non-zero constant term because the functions are bipermutive. So we are always summing the two leftmost and rightmost variables with coefficient 1, which means that we have degree n, and in particular the polynomial is harmonic, and the constant term must always be 1 in this case. In particular, the funny thing was that we got like a recurrence equation, which is already known in the online encyclopedia of integer sequences by many other facts, such as, for example, the collapse conjecture, because if you start from the numbers in these sequences, then it is kind of simple to prove that you can actually converge the periodic solution 1, 4, 2 in the collapse length. In any case, we generalize this also to any finite field F2, so the counting results, and also along with the size of the largest family of pairwise superprime polynomials that we can get. So basically, it is the largest set of mutually orthogonal Latin squares that you can construct with cellular automata. Okay, now for the second part, let's go into the details of the complicated construction which exploits cellular automata and Latin squares. So this is leaning like on an intermediate object, which is an Hadamard matrix. So an Hadamard matrix is basically a square matrix with entries that are either plus or minus 1, and which is orthogonal. So orthogonal in the linear algebra sense, which means that if you multiply the matrix by its transpose, then you get the identity matrix. So a necessary condition for the existence of these matrices is that n must be either 1, 2, or a multiple of 4. Actually, a long-standing upper problem in discrete mathematics is the Hadamard conjecture is whether a Hadamard matrix actually exists for every possible multiple of 4. So this condition is also sufficient. So what is the connection between Hadamard matrices and bent functions? Well, basically, Dillon in his thesis showed that if you have a function of n variables, and then you get like the polar version of this function, so you take like minus 1 to the power of the value of the function f of x, and then you define this matrix H of size 2 to the power of n times 2 to the power of n, so a square matrix. It is defined as the polar version of x, XOR y. So we sum two input vectors, the vector of the row of the matrix and the vector of the column of the matrix. So basically, we have this interesting result that f is a bent function if and only if this matrix constructed in this way is a Hadamard matrix. So it is an orthogonal matrix. This is an example with the simplest possible bent function of two variables that we can get. And then there is a theorem dating from 73, actually even before Dillon's thesis by Bush, who actually shows that if you have mutually orthogonal Latin squares, then you can construct also Hadamard matrices. So the idea is that you start from a set of t mutually orthogonal Latin squares of order n, and then you construct the corresponding orthogonal array. So what is this orthogonal array? Let's go into detail now. Basically, it is n squared times t matrix, where each column of this matrix is basically the linearization of each Latin square. So the idea is that if you have like a set of Latin squares, then you will have here all your rows and columns. And then you start by taking first this row here, and you put it as a column in here. So this will go here. Then you take the second column here, and you put it here, and you continue in this way. And you do this for all possible Latin squares in your family of modes. And you get what is called an orthogonal array of strength 2, which means basically that if you take any subset of columns in here, then you will see all possible pairs in the Cartesian product exactly once.
Sorry, I didn't understand. You take the rows and then you flip them, and then you make a column out of them.
Yeah, it's like you take all rows, you put one next to the other, and then you take the transpose. That's the same thing. So you just go in this order. So you go here, and then you go here, and then you go here. Okay.
Thanks.
Yeah. Okay, so as I now I'm not showing you, this is the form of the Hadamard matrix that you can get if you have an orthogonal array that is defined by a set of mutually orthogonal Latin squares. It is a symmetric matrix, and basically it is a matrix of size 4 times t squared by 4 times t squared. Okay, so you can construct with mutually orthogonal Latin squares Hadamard matrices. So now the trick is, okay, but what if, can we just use like any set of mutually orthogonal Latin squares to get like a bent function, because we said that bent functions are associated to Hadamard matrices. The problem is that those Hadamard matrices have a very specific function structure, if you remember. So they are defined as the XOR of the two, let's say the two input vectors that index the row and the column of the matrix, and then you take the polar version of the Boolean function. In particular, you can see that there is a counterexample. So not all sets of T mutually orthogonal Latin squares give rise to Hadamard matrix that has this structure that is required to get a bent function. So this is the smallest counterexample that I know of. It's already quite big. But if you construct like the 64 by 64 Hadamard matrix, then you can see that this does not give a bent function, in the sense that the Hadamard matrix that you construct from here is not a Hadamard matrix with this structure that is required for a bent function. So what about the most, so the mutually orthogonal Latin squares that we can construct with linear cellular automata that I showed you in the first part? So here we are considering in particular only cellular automata over the finite field FQ, where Q is a power of 2, so it's an extension of F2 basically. Why? Because basically we want to get Hadamard matrices where the size is 2 to the power of something, because then that is the ideal setting for the bent function. But also we know from Bush theorem that the Hadamard matrix must be of size 4 times t to the squares, and also it needs to be 2 to the power of n because of the fact that we want a bent function. So we need to take all constraints in consideration. Then we need to get like t coprime polynomials of degree d minus 1, which would be like d minus 1 is the diameter of the cellular automata. If we take the associated polynomials, the degree would be minus 1, the original diameter, because we are starting from power 0 in the polynomial. So basically we have this relation here, which means that we need to get coprime polynomials, t coprime polynomials, which is 2 to the power of w, where w is any integer in particular. So this is the constraint. The number of mutually orthogonal Latin squares need to be a power of 2 in particular. And actually, what we then showed, well, not in the beginning, in the first version that we submitted to BFA, but in the next one that we submitted to CCDS, we actually showed that if we construct the mutually orthogonal Latin squares which satisfy this constraint of being 2 to the power of w, then actually the Hadamard matrix that you construct using Bush theorem has exactly the structure of a Hadamard matrix related to a bent function. So basically we started from linear cellular automata and coprime polynomials, and we arrived at the end to a bent function through Latin squares, orthogonal arrays, and Hadamard matrices. Notice that here the linearity of the cellular automata, so the fact that the linear rules, the local rules are linear, is crucial to grant this result. So if you get like nonlinear bipermutive cellular automata, this does not hold in general. So it is very important to take the linearity of the local rules. And actually this costed us our first project in BFA. So we were missing this detail in our proof. So this is an example. Again, if we use the two polynomials, 1 plus x squared and 1 plus x squared, which are rules 90 and 150 with the cellular automata that I showed you before. So you get these two orthogonal Latin squares. Then you get the orthogonal array, which is like the linearization on the column. So here you see like this first column is related to this Latin square, and this column is related to this Latin square. And then you construct the resulting Hadamard matrix with Bush theorem. Then you take either the first row or the first column as the truth table of a Boolean function. So like here, basically you say, if it is plus, then you take a 0. If it is minus, then you take a 1. Okay. Then this truth table maps to this Boolean function with this algebraic normal form, which is a band function. Basically, it is the canonical form of the band functions in 4 variables in particular. Okay, so after that, so let's recap a bit. So we start with a family of T coprime polynomials. Like in this case, we only need 2 coprime polynomials with n equal to 4. Then we use this to define like the local rules of linear cellular automata, and we construct the corresponding Latin squares using this trick of using the first half to index the row, the second half to index the column, and the output to index to encode the entries at those coordinates. These are orthogonals, and then we get the Hadamard matrix using Bush construction that goes through the orthogonal array characterization. Then we get a band function. So what we consider more in our submission to CCDS was basically the existence question. We say, okay, suppose that we get any even n. So are we always able to find a large enough family of coprime polynomials that can be used to be put it like in this pipeline, in this construction, to get always band functions? And then if this is the case, how many of this family does exist? So how many band function can we construct with cellular automata? So it turns out that for the existence question, basically you always get a large enough family if and only if the degrees of the involved polynomial is only 1 or 2. So for higher polynomials, you don't get enough coprime. For higher degrees, you don't get enough coprime polynomials to apply this construction. And then these are the formulas that you get for the 2 cases. So for degree 1, you get this simple binomial coefficient. For degree 2, you get something which is uglier, but it can still be used to define how many functions you can get with this construction. An important remark that was noticed by one of the reviewers is that each family can always be augmented with the 2 polynomials 1 and x to the b, because even if these do not satisfy the constraint of bipermutive cellular automata, it is actually simple to show that they are always coprime with any family of coprime polynomials where each polynomial has a non-zero constant term. So we can always, let's say, augment this family at least by 2 polynomials. Okay, now this is very complicated, and it was like observed by several reviewers during our publication process at Design Codes and Cryptography in CCDS. So now let's see like a simplified construction for this construction here. So like I said, first attempt was BFA, it was rejected because the proof was incomplete. Second attempt, CCDS again rejected because, okay, the proof now is correct, but the construction is very complicated. And actually, you are not guaranteeing that the band functions that you're constructing are really new. So if they are already belonging to some known classes or to some unknown classes. Third attempt, we tried to tone it down a bit more, our claims, and saying, okay, we don't know whether these functions are new, but at least it is like a different way of constructing band function, which might be interesting to see in the future. So we got major revision at DESI. And the funny thing was that it was maybe the best review that I actually got from all the papers that I submitted, because it was at the same time the most enthusiastic and also the strictest one. So the review started like this: this paper must be published absolutely in some form, because it has the potential of becoming like a major references on band functions, but not in this way. Like you need to scrap off all the thing on cellular automata, mutually orthogonal Latin squares, Hadamard matrices, etc. Because actually you can, so he showed us, or she showed us, a simpler construction using what is called linear recurring sequences. So what are linear recurring sequences? So basically you get a sequence of integer, not integer numbers, of elements from a finite field F2, and it is infinite, so like the index is like over to natural numbers. And these elements in the sequence satisfy a linear relation. So very simple. Actually, these linear recurring sequences can be computed with what is called linear feedback shift register in computer science. So you know, when you start studying cryptography, you say, yeah, there are several ways to construct pseudo-random number that are important for cryptography. For example, linear feedback shift registers, but yeah, okay, you don't use that because it is really crappy. Like you can predict linear feedback shift register, the numbers that it can generate in a very simple way using a bit of linear algebra. So usually, for example, you have Boolean functions to combine, to mix a bit the output of several linear feedback shift register and so on and so forth. In any case, for our concerns, basically what it interests us is that a linear feedback shift register or linear recurring sequence has a feedback polynomial associated, which is again similar to the case of the linear rule of cellular automata. It's like a polynomial that takes the coefficients of the linear recurrence and use it as coefficient of the monomials in the polynomial. But actually, if we now consider, let's say, the set of all sequences that satisfy a linear recurrence that has a feedback polynomial f of x, then you can show that this set, this family, is actually a vector space. Okay, it satisfies the axiom of a vector space. And then if you take the projections of these sequences onto their first 2D coordinates, so you just truncate, sequences are infinite, but you just truncate them up to the first 2D coordinates, then what we get is a d-dimensional subspace of fq to the power of 2 times d. And this subspace is actually the kernel of a linear map that goes from fq to the power of 2d to fq to the d. And this is the, let's say, the form that you can see here is the, let's say, is the form of the linear map for each possible output coordinate. So for each possible output coordinate I, we get this particular linear function that computes our linear map, one coordinate of our linear map. And the matrix that is associated to this linear map is like this one. But this is actually, okay, with a little bit of tweaking, but it is exactly the global rule of a linear cellular automaton. So basically, they're the same thing, linear recurrent sequences and linear cellular automata in a sense. So basically, we can recast, like we can rewrite our, let's say, our results from the previous version using cellular automata using coprime polynomials and linear recurring sequences. So the original theorem that said, okay, if you have two coprime polynomials and then you construct a linear cellular automata with Latin squares, then these Latin squares will be orthogonal. Then this translates in the realm of linear recurring sequences as if you get two polynomials of degree higher or equal to greater or equal to 1. Then the kernels of the linear maps that you define as the projection of the first 2D coordinates in the families of all sequences satisfying their respective linear recurring sequences. Then the kernels of these two linear maps will have trivial intersection if and only if these two polynomials are coprime. Okay. So what is the consequence? The consequence is that if you have a family of t pairwise coprime polynomials, then you can define a partial spread, which is actually what we can use to define a band function in the partial spread class. So what we showed in this way is that all the functions that can be constructed with cellular automata are actually in the partial spread class. And in particular, you remember that we said, okay, these families of coprime polynomials exist if and only if the degree is either 1 or 2. So for 1, what we showed is that these functions are actually coincides with the Desarguesian spread, so the function in the Desarguesian spread, which is also called the classic SAP, from AP is a fine plane. Basically, you can define the Desarguesian spread in this way. So this is the definition. You start with a subspace, which is a subspace of the Cartesian product of f2 to the m by f2 to the m. Okay. And then if we consider, on the other hand, the form of the linear map of our linear recurring sequences, in the case of degree 1, then we get this expression here. But this is basically, if we are going to get like the kernel of this linear map, then we will get exactly one element in the Desarguesian square, if you do the algebra in between. Basically, what we showed is that our construction for degree 1 with polynomials of degree 1 coincides with the class PSAP. And then they said, the reviewers say, yes, okay, but you should show that these functions, at least some of them are unknown, or you don't know what is the current status. Okay, so for degree b equal to 1, we already know that they are already known, in a sense, sorry for the pun. But actually, we computed what is called the two ranks of these families, of these bent functions that we can construct with degree 1. The two rank is basically the rank of the translate design. So you take a Boolean function f, then you construct a matrix which is defined as f of x, x, or y. So x is again the row and y is again the column of this translate design of this matrix. And then you compute the rank of this binary matrix. Basically, the nice thing is that you can, this was showed by Wang et al. In a paper in 2007, you can use the rank to tell apart inequivalent functions. So equivalent function in the sense of extended affine equivalence have the same rank. So if they have the same rank, then they are equivalent. So if they have different ranks, two ranks, they are inequivalent. This is the case of the functions PSAP that we get with polynomials of degree 1 in our construction. And what we got here is basically a verification of the counts that were already performed by Wang et al. In their paper, and actually an extension, because here we consider also an additional polynomial that they didn't consider in their family. So we actually extended them. But the most interesting thing, and this is the last result that I'm showing you before concluding, is the case of degree 2, because for degree 2, actually there is no straightforward way. For sure, they are not like in the, let's say, they cannot be transformed into the same expression as for the Desarguesian spread. So we say, okay, these are good candidates for saying maybe these bent functions are really new or unknown. And actually, if we're going to compute the distributions of the two ranks for this function in 8 variable and polynomials of degree 2, so in this case, we need 8 pairwise coprime polynomials if we want functions in the class PS minus, or T plus 1, 9 for PS plus functions. Then we construct all the translate designs, we compute the ranks, and then basically we count how many functions have which rank, okay? So Wang et al. Actually showed that if you take functions of 8 variables, then the upper bound for functions that are in the class PSAP, which is already known, is 42 in this case. And you can see here that both for PS minus and for PS plus, we are getting something which is above 42. We have 44 and 46. So these are actually both inequivalent to Desarguesian partial spread functions and also to Maiorana-McFarland functions, because in this case, Maiorana-McFarland functions have an upper bound on their rank, which is 30. So actually all of these functions of degree 2 are inequivalent to Maiorana-McFarland functions. And this is it. So to conclude, basically, so this was kind of complicated constructions of bent functions that started with cellular automata, Latin squares, and Hadamard matrices, but actually that can be simplified thanks to the reviewer of Daisy, I must say, because we wouldn't be, we were so involved in that construction that we couldn't see like this simplification that was kind of not trivial, but let's say it's much more natural in a sense. And it is based on the kernels of the subspace generated by linear recurring sequences. And if we consider, since we have this function only for polynomials, pairwise coprime polynomials of degree 1 or degree 2, for degree 1, then this bent function coincides with the class PSAP, PS affine plane, which is already well known in the literature. For many functions defined by polynomials of degree 2, they are not in PSAP. We can show it like for 8 variables, so likely it will be the same thing also for higher number of variables. And actually this gives us like the open problem, which is very natural, okay, but these functions that are not in PSAP, are they actually new or are they equivalent to other function in the partial spread class that are already known to be inequivalent, because there are many constructions in the partial spread class. The problem is that it is very difficult to find, actually, as far as I know, there are no works that try to construct like the distribution of the two ranks, for example, of all known function in the PS class in general. So it is difficult because you need to do it, to code it from scratch and do all the experiments for checking inequivalence. Also, it would be interesting to see like this, if this characterization with cellular automata can still be used, for example, for efficient implementation of these then functions in certain symmetric ciphers using linear feedback shift registers. And also, one theoretical question is, here we started with families of coprime polynomials, where each polynomial is of degree d and has a non-zero constant term. And then we augmented all of these families with the polynomials 1 and x to the power of d, okay? But actually, this constraint started with our cellular automata version of the work. So what if we say, okay, we start actually with any family of pairwise coprime polynomials with no constraint, we just put the constraint on the degree, for example, or not even the degree, actually, even the degree could be dropped, to be honest. Can we actually get more functions than what we get with this, let's call it constraint construction? And that's it. Thank you for your attention. These are a bit of references. If you have any questions, I'm happy to hear them.